Have you ever thought about how a beam of light could act like a microscopic scalpel? Well, today, we're digging into a very specific breaking point where light has just enough energy to literally tear an oxygen molecule in two. And it all comes down to a powerful secret that light is hiding.
It's a pretty good question, right? I mean, if sunlight is blasting the Earth with all this energy, why aren't the molecules in the air, or even in you and me, constantly being ripped to shreds? Well, there's a reason, and that's the mystery we're going to solve today.
So, what is this big secret? The first thing we have to get our heads around is that light isn't just for seeing stuff, it is energy. And how it delivers that energy? Well, that changes everything. You see, light doesn't just flow smoothly. It comes in these tiny, individual packets of energy called photons. Think of them like little energy bullets. But here's the kicker. Not all photons are created equal. Their power, their punch, is all tied to something called wavelength.
And look, this isn't just some vague idea. It's a fundamental law of physics. There's an actual equation that acts as the rulebook, perfectly linking a light wave's properties to the power it's packing.
Okay, don't let the symbols here scare you. Just focus on this one key relationship. E, for energy, is connected to that little lambda symbol on the bottom, which stands for wavelength. And because wavelength is in the denominator of the fraction, it means they have an inverse relationship. When the wavelength gets shorter, the energy of that photon goes way up.
And this right here is the main takeaway. A photon with a short wavelength, like from ultraviolet light, packs a serious wallop. But a photon with a long wavelength, like the visible light we see with, has a much weaker kick. You know, it's the difference between getting hit by a major league fastball and a slow-moving beach ball.
So let's bring this all back to our main character for today, oxygen. The O2 molecules that we all breathe are held together by a pretty strong chemical bond. And just like anything else, that bond has a breaking point. There's an energy cost you have to pay to snap it. And that price tag is incredibly specific. It takes exactly 498.4 kilojoules to break 1 mole of oxygen molecules. And a mole is really just a standard way for scientists to talk about a ginormous number of them. Think of it like an admission fee. A photon has to pay this exact price or it doesn't get in.
And here it is. This is where it all clicks together. Using that physics equation we just saw, we can figure out exactly what kind of light carries that much energy. And it turns out that 498 kilojoule requirement is met perfectly by a photon with a wavelength of 240 nanometers. That is our magic number. That's the line in the sand.
So, when a photon actually hits an oxygen molecule, the molecule faces this use it or lose it moment. It absorbs this burst of energy, but it only has a tiny fraction of a second to do something with it, and there are really only two ways this can go. No matter which path it takes, the very first thing that happens is the molecule gets kicked into what we call an electronically excited state. We show this with a little asterisk. Now this is a super temporary, really unstable condition. The molecule is just buzzing with all this extra energy, and it has to get rid of it, one way or another, and fast.
Okay, let's look at path number 1. This is what happens when a photon with a wavelength longer than 240 nanometers hits the molecule. So it's a lower energy hit. The molecule absorbs it and enters that jittery, excited state. But because the energy isn't enough to break the bond, the molecule just kind of shudders, releases that energy as a tiny puff of heat, and goes right back to being a normal O2 molecule. Nothing breaks.
But now for path number 2, a high-energy photon, one with a wavelength of 240 nanometers or shorter, comes screaming in and strikes the molecule. Again, it gets kicked into that excited state, but this time the energy it absorbed is greater than the bond's breaking point, so that energy is immediately used to snap the molecule apart. This is called photochemical dissociation. The O2 molecule is gone, and in its place, we have 2 separate oxygen atoms.
So, everything we've just gone over, it really boils down to this one simple, powerful principle. It's a clear line in the sand drawn by the fundamental laws of physics.
So let's recap the rule. An oxygen bond has a specific price tag, and only photons with a wavelength of 240 nanometers or shorter carry enough cash to pay that price. Any photon from a longer wavelength is just too weak. And this part is absolutely critical. The molecule can't save up energy from a bunch of little weak hits. It has to get the full payment all at once from a single powerful photon. It's an all-or-nothing deal.
You know, this whole principle doesn't just apply to oxygen way up in the atmosphere. It governs countless reactions all around us, from photosynthesis making our food to the dye in your t-shirt fading in the sun. Which leaves us with a really fascinating question to think about.
What other chemical reactions, maybe ones that are essential to our world, are just sitting there, waiting for a photon with just the right amount of energy to come along and kick them into action?